Good afternoon, and thank you for joining me at IoT World. My name is Jared Eldridge. I'm an applications engineer with the Aanarogudibais's IoT Technology Group. And today I'll be showing you two demo applications utilizing our ultra-low power microcontroller platforms. On the left, I have our IoT asset health tracking demonstration. In this demo, I have a wireless sensor node designed to be associated with a package being shipped, where we can notify either the recipient or the vendor in the event that a package is damaged during shipment. This ultra-low power wireless sensor node has been designed to operate for approximately a decade on a button cell battery. It does this by utilizing the low power characteristics of our ADUC M4050 microcontroller. This is a Cortex M4 with floating point, boasting 680 nanoamps of hibernate current and a 40 microamp per megahertz active current. We keep that microcontroller in hibernate nearly all of the time. We also use an ADXL 372. This is a high G, low power accelerometer with a threshold detection mechanism and an instant on feature. That instant on feature enables us to wake up the accelerometer, to capture the data, including the initial impact event of interest, and to fill that FIFO up such that the microcontroller can drain it out and observe from the moment of impact and the following accelerometer data exactly what's happened to your package in transit. This demo also utilizes the ADF7030-1 ultra-low power transceiver. This is a sub-gigahertz ISM band transceiver operating in a range of about 400 to 900 megahertz. In its hibernate state, it's drawing about 10 nanoamps. This entire wireless sensor node is operating at about 2.1 microamps total system current. That's 1.2 microamps for the accelerometer, 10 nano for the radio, and about 680 nanoamps for the microcontroller. In this way, the application runs for about a decade on a button cell battery. In the event that the package is dropped and the accelerometer wakes the microcontroller, we drain the FIFO. We perform some basic computation to determine whether the package landed on flat, on its edge, or on its corner. We can determine whether the package may have been damaged. If so, we power up the transceiver and send data across to our gateway device. The gateway device is not expected to be energy constrained. In this demo, we're in a constant receive mode, drawing about 25 milliamps. In the event damage has been observed, the gateway device is informed. It's connected to the cloud, for example, through a satellite link on a cargo ship or similar. That data is sent off and it will inform either the recipient or the vendor that there's been some damage in flight. Take, for example, this demo environment here, where we have these demo booths themselves. The value to us of knowing prior to demo day here that this wall was damaged, it's invaluable. If we could, we'd like to know 2 or 3 days in advance so we can order replacement parts, or that the vendor themselves could actually ship us replacement parts before we unwrap them on demo day. I'd like to show you our second demonstration. This is our remote toxic gas demonstration. Unfortunately, this was damaged on shipment to me. It was shipped along with our IoT asset health tracker, and ironically, that damage was not recorded as the batteries were removed. But what a great demo that would have made. Thankfully, I can still talk about the ultra-low power characteristics and how we enable applications such as this using our ultra-low power ADI Cup 3029 platform. In this case, the toxic gas sensor is on this generic board with which we can use any number of toxic gas sensors. In this case, we have a carbon monoxide sensor from AlphaSense. This is implemented on an Arduino form factor board, plugged into our ADI Cup 3029. I have another instance of that 3029 board here for your view. This board utilizes the ADUC M3029 microcontroller. This is a Cortex M3 part, boasting a 750 nanoamp hibernate current and 30 microamp per megahertz of active current. With this board, we regularly create applications for our customers with an average system current between 3 and 5 microamps by utilizing our sensor strobe and other low power technologies. This board enables rapid prototype iterations by providing Arduino, PMOD, and Grove connectors, so our customers can utilize the same sensor boards and other equipment they're currently using on Arduino type platforms. But unlike those Arduino type platforms they're using today, drawing tens or hundreds of milliamps of current, with this board they can draw such little current they can actually create a demo application they can reliably hand to their customers or to their venture capitalists or to whomever they need to impress, that can run for years to decades on a set of AAA batteries. Thank you very much for joining me. For more information, please visit analog.com.